So here you find an extra exercise which is not in the lecture notes, but that can be useful. As usual, in this course, there are no assignments. So if you want to solve it, good. If you don't want to solve it, good as well. Obviously, if you have questions, feel free to ask, either during the break or you can come to my office. Most of the time there. The exercise says the following. It's a nice exercise because it allows to already solve an Ito integral, which is also a rather useful one, without using the Ito-Doeblin formula or the Ito-Doeblin theorem or lemma. It's called in 20 different ways. The exercise tells the following. Consider the Ito integral between 0 and capital T of bt omega, where b is our Brownian motion, dbt omega. So we want to integrate the Brownian motion with respect to itself. We take our usual partition of the time interval 0 capital T, and as usual, we assume that the mesh of this partition vanishes for n going to infinity, so it's the standard framework. What I ask you to verify is that I can define a sequence phi n, which is an approximating sequence. That is to say, it satisfies that condition to be an approximating sequence. And that sequence can be defined as follows. Phi n of t omega is equal to the sum for j from 0 to n minus 1 of btj omega, indicator of the interval tj plus 1, and obviously t. And after showing that it is an approximating sequence, if you just try to exploit the properties of the Brownian motion, so every time you have, for example, the expectation of the increment, you know it is 0. When you take the expectation of the second moment of the increment, then you know it is the length of the time interval. So if you combine these things, you should be able to end up with the actual solution of this integral, which is 1 over 2, so 1/2, the Brownian motion squared in capital T minus t over 2. You will see that this will be actually the solution that we get with the Ito formula. So let's say that this is the long and cumbersome way to reach this solution, but it's a nice exercise. Okay, so we have these three lemmas. We have these three lemmas, which are not difficult. So in a sense, it's always the same stuff. We have to find the proper element to define the approximating sequence, and then at the end of the day, we end up applying the dominated convergence theorem, and we find the limiting behavior that we want. And we do that for bounded and continuous functions, for bounded functions, and for whatever function in the M2 class. So I will leave the proofs that you will see. They are short, not particularly complicated, of the different lemmas to you. Actually, in the lecture notes, you find just the proof of the first and the third lemma. The second one, I removed that just because it's in line with the first, and it's just a little bit longer, and I think there is already enough material in the lecture notes without that proof. But if you want to know that, come to my office, and I can bother you with that. So I leave the three proofs for you, but the only thing that I want to underline is that, for example, in the first lemma, that is the one that deals with approximating a bounded and continuous function with a sequence of simple processes, you see a trick that then appears also in this exercise. And the trick is the following. If you want to define the sequence of your simple processes, T omega, that approximate, remember, a function g in M2 which is continuous and bounded. Interestingly, a very simple way of defining that type of simple process is to use g itself. And how? By defining the simple process in this way. The sum from 0 to n minus 1 of g tj omega, the indicator of tj plus 1 t. That you see is in line with also what we do here. So we are essentially cutting our g, which is possibly a random function. If it is deterministic, then it's evident, okay, nothing to say. But even if it's a random, we just cut the function into pieces and we build back a process that is just the sum of these pieces. And then using this process, you can apply the dominating convergence theorem and you find the result. So it's a quite standard way of approaching at least the bounded and continuous functions. Okay, given that we assume for the moment to have proven the theorem, so we know that the theorem works, that is to say we can always find this approximating sequence of whatever function in M2, we can give actually the definition of our Ito integral. And the definition is the following. If f is a function, generic function in M2, and phi n is an approximating sequence of simple processes in M2, obviously implicitly for f, so it's an approximating sequence for f of simple processes in M2, then the integral between 0 and capital T of f t omega d b t omega is defined as the limit of 0 t phi n t omega dbt omega. So we define our Ito integral as the limit of the sequence of Ito integrals for simple processes that we have already studied, and that's it. So it's a limiting definition. The fact that this sequence exists comes from the previous theorem that, as I told you, can be proven directly for the simple processes, but I think more wisely and in a simpler way, you can split into categories of functions, but at the end, you always have these simple processes coming out. So if I have a function f, the theorem that we just stated says that there exists an approximating sequence, and if there exists an approximating sequence, then we can define our Ito integral for our function f as the limit of the sequence of the Ito integrals of the simple processes. Now, from this definition, we can immediately inherit a lot of nice results. For example, proposition, the expectation of f t omega d b t omega guess what? Is 0. So if I take the expectation of a generic Ito integral, and remember now we are taking f, is no longer a simple process, it's a generic f in the M2 class. Then if I take the expectation of this guy, this expectation is equal to 0. Now, how can we prove that? In the following way. So let phi n be an approximating sequence of simple processes for f. And again, they are both in the M2 class. Okay, even if I don't say that, we are always in the M2 class. So it's an approximating sequence of simple processes for f. Now, what do I know? Then I know, exploiting essentially the definition of our Ito integral, that the limit for n tending to infinity of 0 t phi n dB is equal to 0 t f dB. Okay? This is just and since phi n is also an approximating sequence, what do we know? We know that this convergence is in what? It is in quadratic mean because of the properties of the approximating sequence. But if this is true, we immediately know something thanks to the convergence in quadratic mean. We know that if I take the expectation of phi n dB, this expectation will converge to the expectation of 0 t f dB. Because my f phi n are elements of an approximating sequence for f. So we have this convergence in the expectation. But now, since these are all simple processes, what do we know about this expectation? Is 0. So the expectation of the Ito integral for a simple process we have proven last time is 0. Okay? Why? Because I can just substitute the definition of simple process, then I can use the measurability to split the A part from the increment of the Brownian motion. It means that the expectation of their product is just the product of the expectation. The Brownian motion increment has expectation 0. Everything is 0. So what I have a sequence of zeros that approximate something. So it means that this guy needs to be 0. Okay? So I have zeros that approximate something that needs to be 0. Otherwise, makes no sense. In the same way, and this is an exercise that you find in the lecture notes, you can prove the Ito isometry. Always exploiting the convergence and the fact that you are playing that our Ito integral is defined as the limit of the integrals of simple processes that are an approximating sequence for our function f, so that they have these nice property in terms of convergence. And the Ito isometry tells us that if I'm interested in taking the integral of f dB squared, this is equal to the expectation of 0 t f squared dt. So the same result that we had for the simple processes. And if you take two functions, f1 and f2, that are generic functions, and you take the expectation of the product of their integrals, then the result is the expectation of the integral of their product. And these are fundamental quantities when we play with the variance, the covariance, the correlation, as we shall see. Because, for example, we might be interested in computing what is the variance of the price process. what is the variance of the return process. But if we have different price processes, if we have different return processes or value processes in general, we are very often interested in computing their correlation to see if they are dependent. By the way, because from next time we will do that over and over again. So little digression that comes back to probability 101 or statistics 101. If I have X and Y and they are correlated, what do I know? Are they dependent? If they are correlated, if the correlation between X and Y is different from 0, and you know that the correlation lies between -1 and 1. So it's different from 0. Are they dependent? No one?
Yes.
Yes. And you can be wrong. I mean, even if you say something, I totally don't care, and I have a sort of golden fish memory for this kind of thing, so I don't remember that. For sure, not an exam. So feel free to be wrong. So if they are correlated, they are dependent. That's true. But they are dependent in general, or is a specific type of dependence? Because that's the most important thing. So they are dependent. Yes. Yes, I mean that if I have my X and I have my Y here, and I have a sort of scatter plot, they tend to behave in this way. Okay, so the cloud has some sort of inclination like this, and it means that they are linearly dependent. Okay, correlation is linearly dependent. It means that more or less I can always find some sort of line between the two that represents the dependence. Okay, and again, I know you all know this, but I say that for myself, not to forget that correlation is not the slope of the line. Okay? Correlation is a measure of how well a line, a generic line, describes the dependence. So correlation 0.8 does not mean that the slope is 0.8. Correlation 0.8 means that the dots are very, very close to the line, whatever line. It can be this line. So let's say correlation 1. Correlation 1 means that essentially X and Y are in a perfect linearly dependence. It means that if I have X, I immediately have a Y. That can be 3X plus 2, I don't know. Okay, but there is a linear dependence between the two, and it's precise. And that line can be this, can be this, can be this, and correlation is always 1, because all the points are on the line. If it is -1, it will be this, it will be this, it will be this, because they are all on the line, but the line has a negative slope. Correlation 0.3, it just means that maybe the line is this one, maybe the line is this one, but the dots are not on the line, they are scattered around. The smaller in absolute terms, so the closer to 0, it means that the cloud is larger. So there is more variability around this line. The higher, it means that you are more on the line. Correlation equal to 0, it might mean different things. Either there is no dependence, because the line is a cloud, it's a globe, it's a circle of points, so that if the points are exactly in a circle like this can be the line, this can be the line, this can be the line, this can be the line. So it's difficult to find the linear dependence. But correlation equal to 0 does not guarantee that they are independent. They can be independent, and probably they are independent in specific situations. So under a Gaussian world, so a world in which everything is normally distributed, we will have that uncorrelated means independent. And that's why they use, and we use a lot, the normal distribution. But I will criticize that a lot, because I mean, probably you know that I'm interested in extreme value theory, so in the tails where normality does not hold, okay? So, but if you assume normality, uncorrelated means independent. But not in general, because if I have a quadratic dependence like this, even a perfect one, between X and Y, correlation from a theoretical point of view is 0. Why? Because they are not linearly dependent. They are quadratically dependent, maybe cubically dependent. So we have to find other measures. So also the Ito-isometry will be useful when we assume a linear word. If the word is not linear, we will have to say something more about the isometry part, okay? But in any case, if you do not remember well, correlation, uncorrelated, that uncorrelated does not mean necessarily independent, please refresh that part because it's very, very important to us. Okay, so we can prove that the expectation is equal to 0. We can prove the Ito-isometry, whatever you want. You can prove that it's a martingale with respect to that wherever, if you consider whatever Ito integral, okay, this object here inside the expectation, this guy here, it's a martingale with respect to the natural filtration generated to the Brownian motion and with respect to the probability measure that governs the Brownian motion. So P for us is P. Again, the spoiler of the course is that there are situations in which maybe we have a Brownian motion, which is a strange Brownian motion because it has some sort of drift. So it's a Brownian motion with drift. And in a Brownian motion with drift, you lose some nice properties. What we will find is to change the measure such that our Brownian motion with drift by magic becomes a standard Brownian motion. And then we can come back to all these nice properties. A last that we do not consider for the moment, so it's important to state it, but we will not prove it for the moment. If we end up, if we have the time at the end of the course to do some things, then I will be back also to the proof because it's important to understand what we possibly do. But for the moment, it's overdue. But the proposition is the following. It's proposition 5, I guess, in the lecture notes. Yes. It means that if I consider a generic Ito integral for a generic function in the M2 class, then you know that it's a random variable. The Ito integral is per se a random variable. If I integrate with respect to different t's, it becomes, if you want, a stochastic process. But it always admits, and this is important, a continuous modification. So every Ito integral allows for a continuous modification. It means that I can build an auxiliary process that have some nice stochastic properties, not processes, with respect to my Ito integral. But we will be back if needed. By the way, it's nice to remember that. Okay, let's see if in the last 20 minutes we are able to say something about the Ito formula. What we will now introduce is a slightly more general class, which is called the H2 class. All the results that we have proven within the M2 class hold or can be easily adapted to the H2 class. And from now on, in this course, everything will be in the H2 class. The H2 class can be further generalized, but we ignore that. Now, a function f belongs to the H2 class if, and obviously it's a function that for us maps from 0, infinity times omega to r, as usual, but our function is in the H2 class if f is b times f measurable. So it is exactly the same requirement as for the M2 class, where f is the sigma algebra of our probability space, and b is the Borel sigma algebra on the non-negative semiline. Okay, so that part exactly remains the same. Then there is a second requirement, which is already interesting, and it says that it exists a process MT, so this is an M, like Mark, MT, such that the Brownian motion BT omega is a martingale with respect to it. And obviously, this guy will be contained in our sigma algebra F. So there is a filtration, MT, that is included in our sigma algebra, and such that the Brownian motion we are playing with is a martingale with respect to that filtration and obviously the probability measure. Now, it's evident that I can take the natural filtration generated by the Brownian motion, and that works. But in general, I can also think of other filtrations. Other requirement, Ft omega is MT measurable. So what does it mean? It means that, again, we have a non-anticipating component. Now, instead of necessarily the natural filtration generated by the Brownian motion, we have this filtration. But still, with respect to this filtration, we have the measurability, so the process is adapted to that filtration and is non-anticipating. So this is exactly the same stuff. Finally, we have a last property. The last property is a relaxation of the property that we saw in the M2 class. You remember we were requiring the finiteness of the expectation of f squared dt, of the integral of f squared dt. Here, what we require is a little bit different. So we require a condition in probability. That is to say, we want the probability of the integral 0 t f squared dt to be finite, to be equal to 1. If our f is satisfying this, so and it lives in this word, it is in the H2 class. And the H2 class is from now on what we will use. Again, as I told you, what we have seen in the M2 class works or can be adapted in the H2 class. Now, we need a few definitions, and then we can state the Ito-Doeblin formula. You will see that also in the lecture notes there are some examples of use of the Ito-Doeblin formula. But since this is not a course in stochastic calculus per se, obviously we just consider some basic results that are useful to us, and then we will see the application of the formula for processes that we actually use in finance. So like, for example, the geometric Brownian motion. Okay, so we want to play with the geometric Brownian motion, and we apply the Ito formula to that. Now, a couple of definitions that are the following. The first one is the definition of stochastic integral, just to be precise, but it's something that by now we implicitly have. So let BT omega be a Brownian motion on omega F okay? A stochastic integral is a process xt on omega fp such that I can write xt in the following way. Xt is equal to x0 plus the integral between 0 and t of us omega ds plus the integral between 0 and t of vs omega dbs omega, where u and v belong to H2, and for what concerns u, there is also an extra condition, which is the following. The probability that the integral of u s omega ds is finite is equal to 1. So on u, we also require a first moment condition, if you want. It's not only about something that implicitly requires the second moment, but is also on the first moment. So I have that u and v, this is u and this is v, are in H2, and for what concerns u, I also have that the probability of the integral between 0 and capital T of us omega, in absolute terms, ds, is finite, with probability 1. Okay, this is our definition of stochastic integral, which is a stochastic process. And if you remember the way in which we started last week, we were playing with this guy, Pt. And at a certain point, we were figuring out this sort of solution for our differential equation. And then our problem was that we were not able to play with this term. So we had to introduce the Ito integral. So what you will see is that the more content we add, the more the different parts will come together. And now we are just at the second class. Okay, so this is the first definition that we need. The second definition is the definition of stochastic differential. And it's the following. If xt is a stochastic integral, its stochastic differential is dxt equal to ut omega dt plus vt omega ddt. This would be our stochastic differential. What will be clearer, I hope, in the next classes is that all the stochastic processes we will play with the geometric running motion, every transformation of every common transformation of the running motion. So everything that is representable as an Ito process is something of this type. So what changes is that obviously the function u, the function v will be different. But if you think of the geometric running motion, if you think of the different processes that we can use in interest rates, like affine models, like the Vasicek, they all fall in this framework. So once we have the definition of stochastic integral and stochastic differential, essentially we have all we need to introduce the Ito formula, the Ito-Doeblin formula. The Ito-Doeblin formula, essentially, as I told you, is this sort of stochastic counterpart of the chain rule. And the idea is that, imagine I have a process x. So imagine that I have a stochastic integral x that I know, and imagine that I define a new stochastic process y, which is a function of x. So the idea is that I have my process xt, that is a stochastic integral, and then I introduce some function g, such that I can define my new process yt as some g of t xt. And the question is there a way of moving from one process to the other? So is there a way of solving the y process? Or it can be the situation in which, if I know already the solution of the process y, is there a way in which I can come back to the solution of the process x? So the answer to these questions is the Ito-Doeblin formula. So it allows us to have these technical tools to solve this type of questions. So to find the solutions of our process y and to link that to the solution of the process x, or if you want, vice versa. The difficult, if you want, part of using the Ito-Doeblin formula typically is in identifying correctly the function g, because it may not be given explicitly. Okay, in exercises maybe it's given, but otherwise you have to figure out what type of function g you need. And very often, since you may want to solve this starting from a process that is relatively simple, like the Brownian motion or whatever you want, you also have to make educated guesses on the functions u and v. And there, it's a little bit more cumbersome. As the positive thing is that, as for ordinary differential equations, there are classes of solutions. So that if you can try to recognize some sort of behavior in your equation, you can try to find the proper solution. The bad news is that there are many more special cases, and sometimes they are analytically not particularly friendly. Okay, what is good for us is that in this course we will always play with treatable things, but they can be extremely complicated in a few steps. So it's not something very, very nice. If you are interested in this, in going deeper into the different classes of solutions, obviously you have the stochastic differential equation course. So the SD course that plays with that. But I think that it is time to stop. So next time we start directly from the Ito-Doeblin formula. So please arrive to this type of definitions. We briefly consider the Ito-Doeblin formula, maybe discuss a couple of quick examples, and then we finally enter into the financial modeling. We will introduce what is a market for us, what are the mathematical properties of a market, and we will introduce the risk-neutral measure and all the other machinery that we need. Okay, see you next week.